Hey there, science fans! Today we're diving into the world of electricity with a focus on a crucial concept, RMS, which stands for root mean square. Now, RMS might sound a tad intimidating, but trust me, it's not as complex as it sounds. In simple terms, RMS is a way to measure the effective value of an alternating current, AC, or voltage. Think about it like this. Imagine you're trying to measure the strength of waves crashing on a beach. Some waves are huge, some are small, and they all come and go in a cycle. RMS is like finding the average force of those waves over time. It gives us a more meaningful value than simply looking at the peak of each wave. In the realm of electrical engineering, RMS is a cornerstone for understanding and working with AC circuits. From powering our homes to transmitting radio signals, RMS plays a vital role in ensuring electrical systems operate efficiently and safely. So, buckle up as we explore the ins and outs of RMS voltage and current, uncovering why it's so essential in the world of electricity. Get ready to unlock the secrets of this fundamental concept. Before we dive deeper, let's define what we mean by RMS voltage and current. RMS voltage. Imagine an AC voltage that varies over time, like a wave going up and down. The RMS voltage is the equivalent DC voltage that would produce the same amount of heat in a resistor. It's like finding the average voltage that has the same heating effect as the fluctuating AC voltage. RMS current. Similarly, RMS current is the equivalent DC current that would produce the same amount of heat in a resistor as the fluctuating AC current. It's the average current that delivers the same power as the AC current. In essence, RMS values give us a way to compare the effectiveness of AC and DC sources in terms of power delivery. It's a way to translate the fluctuating nature of AC into a more steady, comparable value. Why is RMS so important in electrical engineering? Well, for starters, most electrical power systems around the world operate using alternating current, AC. Unlike direct current, DC, which flows steadily in one direction, AC constantly changes direction and amplitude. This fluctuating nature of AC makes it tricky to measure its effectiveness using traditional methods. That's where RMS comes to the rescue. By providing an equivalent DC value, RMS allows us to accurately measure AC power. RMS values are crucial for calculating the actual power delivered by an AC source. Design efficient circuits. Engineers rely on RMS values to design circuits that can handle the fluctuating nature of AC without overheating or malfunctioning. Ensure safety. RMS values help determine safe operating limits for electrical components, preventing damage and ensuring user safety. In a nutshell, RMS is like a universal translator for the language of electricity. It bridges the gap between the fluctuating world of AC and the steady world of DC, enabling us to work with AC circuits effectively and safely. Now that we understand the importance of RMS, let's explore how to calculate it. For the most common type of AC waveform, the sine wave, the calculation is pretty straightforward. For a sinusoidal waveform, the RMS value is related to its peak value, the highest point of the wave, by a simple factor. RMS value equals peak value divided by the square root of 2. This magical number, the square root of 2, approximately 1.414, helps us convert between the peak value of a sine wave and its effective RMS value. So, if you have a sinusoidal AC voltage with a peak value of 170 volts, its RMS voltage would be RMS voltage equals 170 volts divided by the square root of 2, which is approximately 120 volts. This means that a 120-volt DC source would deliver the same amount of power as a 170-volt peak AC source. Section 5. Delving into non-sinusoidal waveforms. While sine waves are the most common type of AC waveform, we often encounter other shapes in electrical systems. These are known as non-sinusoidal waveforms. They can take on various forms such as square waves, triangle waves, or even more complex shapes. Unlike sinusoidal waveforms, calculating RMS for non-sinusoidal waveforms requires a slightly more involved approach. We can't simply use the square root of 2 factor. Instead, we need to break down the waveform into smaller segments and calculate the RMS value for each segment. Section 6. RMS calculations for non-sinusoidal waveforms. To calculate the RMS value of a non-sinusoidal waveform, we can use a method called the root mean square method. No surprises there. It involves the following steps. First, divide the waveform into equal time intervals. Next, Square the instantaneous value of the waveform at each interval. Then, calculate the average or mean of these squared values over one complete cycle. Finally, take the square root of the average value. This might sound a bit complicated, but it's essentially a way to find the average power delivered by the waveform over time, regardless of its shape. While the calculation can be more complex for non-sinusoidal waveforms, the concept of RMS remains the same. It provides a standardized way to quantify the effective value of any AC waveform. Section 7. RMS and its role in AC circuits. In AC circuits, where voltage and current are constantly changing, RMS values are essential for analyzing and designing circuits. Here's why. First, power calculations. RMS voltage and current are crucial for calculating power in AC circuits. The power dissipated by a resistor, for example, is directly proportional to the square of the RMS current flowing through it. Next, component selection. When choosing components for AC circuits such as capacitors and inductors, their RMS voltage and current ratings are critical for ensuring they can handle the fluctuating AC signals without failure. Finally, circuit analysis. RMS values simplify AC circuit analysis by allowing us to use familiar DC circuit analysis techniques such as Ohm's law and Kirchhoff's laws with some modifications. In essence, RMS values provide a common ground for analyzing and designing AC circuits, making them more manageable and predictable. Section 8. Practical applications, power distribution. RMS values are deeply ingrained in our everyday lives, especially in power distribution systems. The electricity that powers our homes is typically supplied as AC voltage with an RMS value of 120 volts in the United States or 230 volts in many other parts of the world. This standardized RMS value ensures that appliances from different manufacturers can operate safely and efficiently. In industrial settings where high-power electrical equipment is common, RMS values are crucial for designing and operating motors, generators, and transformers safely and efficiently. Without RMS, it would be incredibly challenging to ensure the reliable and safe delivery of electrical power to our homes, businesses, and industries. Section 9. Practical applications, signal processing. Beyond power distribution, RMS values also play a crucial role in signal processing, which deals with the transmission and manipulation of information in the form of electrical signals. In audio systems, RMS values are used to measure the loudness or intensity of audio signals. This helps ensure that audio amplifiers and speakers can handle the signal without distortion or damage. In radio communications, RMS values are used to characterize the strength of radio waves. This is essential for designing antennas, transmitters, and receivers that can effectively transmit and receive information wirelessly. From the music we listen to the wireless networks we rely on, RMS is silently working behind the scenes, ensuring that signals are transmitted and processed accurately and efficiently. Section 10. Comparing RMS to other measurement methods. While RMS is a powerful tool for quantifying AC signals, it's not the only method. Other measurement techniques include peak value, which measures the highest point of the waveform but doesn't account for its shape or duration, and average value, which represents the average value of the waveform over one complete cycle. However, for symmetrical AC waveforms like sine waves, the average value is 0, which isn't very useful for power calculations. Compared to these methods, RMS provides a more meaningful representation of the effective value of an AC signal, particularly when it comes to power calculations and circuit analysis. Section 11. Conclusion: the enduring importance of RMS. As we've explored, RMS voltage and current are fundamental concepts in electrical engineering. They provide a standardized way to quantify the effective value of AC signals, regardless of their shape or complexity. From powering our homes to transmitting information wirelessly, RMS plays a vital role in countless aspects of our modern world. Its ability to bridge the gap between the fluctuating world of AC and the steady world of DC makes it an indispensable tool for engineers, technicians, and anyone working with electrical systems. So, the next time you flick on a light switch, listen to music, or use your smartphone, remember the silent hero working behind the scenes. Root means square, making our electrical world tick.